Hello everybody, this is Professor Iris Miano. Math 2, Pre-Calculus, Day 5 lecture. We are going to be discussing the procedure of graphing quadratic functions. And so in order for us to be able to graph quadratic functions, we need to go over particular properties of the quadratic function. So I thought that we might revisit the parent function of f of x equals x squared, the basic quadratic, and look at some of the characteristics that it has, and that'll help us be able to expand on these properties in order to have two separate procedures. I'm going to go over two different ways to graph quadratic functions, and then we will look at a quadratic function, and just by looking at it, we're going to take bits and pieces away from it in order to come up with the actual function that governs that trajectory. And then we'll wrap things up with a couple of word problems. So that's going to cover the base that students often are wondering about. What is the point of all of this? Like, why do we care about quadratic functions? Well, they're very good at modeling certain types of interactions, certain behaviors, certain phenomena. So we want to get to know these functions pretty well. So let's start with the most basic one ever, and that's this: f of x equals x squared. Okay, so you might notice that I have a coordinate plane here that goes off into what the highest values are 6 and the lowest ones are -6 in the x and y directions. That's just enough of a space for me to graph this parent function effectively to show you key features in which it exhibits. Okay, so what I'll do is I'll draw myself an XY table, and y of course is also f of x, same thing. And let's go ahead and come up with 5 points that we want to plot. You may notice off to the side, if you're looking, that I have my 5 points ready to go and my curve, cheating a little bit just so that the process of drawing this curve goes smoothly and relatively quickly. But in any event, if I'm going to draw any kind of a curve, and I'm going to use the method of plotting points because maybe I'm not sure about what the shape of this one is, just in case, I can pick the standard 5 inputs for x. And here they are: -2, -1, 0, 1, and 2. And the outputs will be +4, +1, 0, +1, and 4 as well. So you'll notice that we're going to make a little bit of a curvy bit here because we're going to go up, or we're going to start high, go all the way down to the origin, and then curve back up and go high again. Okay, so let's go ahead and allow me to plot these points. Here is the location of -2, 4. It's going to be right there, so that's my first point. Okay, -1, 1 is going to go right about there. Then I'm going to put another point at the origin. That's my 0, 0. Boop. And coming back around, so the 0, 0 is therefore my vertex. This is not a term that's been clearly defined yet, but we will define it, and we have a formula for it coming up in just a moment. Okay, so here is me just plotting these 5 points that I put in my XY table, and then here you'll want to just draw a line connecting these 5 points as smoothly as you possibly can, and this curve, I pre-fit it, should go through all of those things there. You will notice that, here, let me put a little kind of arrow points on either end. That's also a, oops, just kidding. Let's go to, I want to draw, oh, hold on. Why isn't it letting me draw? Hold on just a moment, guys. Okay, I think I figured out what the issue was here. Hold on. Okay, so I think I should be able to draw now. Yes, okay. So my point that I wanted to make here was it's conventional to have the trajectory that you know is going off into infinity be capped with some sort of arrow points. That's all I was trying to get at. Okay, so this is a good representation of the parent function f of x equals x squared, the parent quadratic function, that is. So notice that we have a vertex down here. Let me label it vertex. That is the point at which you turn to go back the way you came, but on the other side of your axis of symmetry. We'll get into that in just a little bit. In fact, I have figures down below that's going to talk about the axis of symmetry, which always goes through your vertex. It's just the vertical line that goes through your vertex. But here it's the origin for the parent function. If you have your quadratic function shifted, it might be somewhere else. Also, you may notice that the parent function is an upward facing parabola, which means it's kind of like exhibiting the shape of, like, you know, an open bowl cross section or something like that. If you have a downward facing parabola, it is resembling a shape of like an arch, okay, you know. And it has a peak if it's an, what's it called? A downward facing parabola. And if it's an an upward facing parabola, it's going to have a trough or a minimum point, okay, like we have here in the parent function. That's an upward facing parabola with a minimum point at the vertex. And if you have it the other way, which we'll see pictures of downward facing parabolas, those have a maximum value. And I'll mention this a little bit later on, but downward facing parabolas are often used to model certain phenomena, because we're more often than not trying to maximize things that we are trying to model. Okay, anyway, so over the axis of symmetry, which in this case is the y-axis, you will notice that one side of the trajectory is the mirror image of the other, and that the corresponding points that occur at the same y value line up perfectly. And that's something that we will be able to use a little bit later on in trying to graph these quadratic functions as they get more and more complex. Okay, so let's keep those things in mind. As far as stretching and compression is concerned, we're going to go ahead and revisit this right here. This was first introduced when we were covering the transformations. And I just kind of mentioned it very much offhandedly that, oh, if you have a scalar multiple, you know, in front of your function, it's going to, depending on its value, stretch or compress. So a stretch is going to look like this, the black trajectory, in which we have a coefficient in front of the x squared being greater than 1, okay? So it's going to get skinnier, which is a little bit counterintuitive in my own mind. I figured that, oh, if I'm going to multiply it by a relatively large number, compared to if I was multiplying it like with the pink trajectory, a coefficient of 1/2, that means I should be making it fatter, right? I'm tripling it, so I should make the, you know, the trajectory look like wider. I don't know. In my mind, that seems to be the connection, but it's a little bit, according to my brain, a counterintuitive relationship, where if you multiply by some factor on your x squared function, some factor greater than 1, you're going to be stretching, pulling it tighter, so to speak. That's the black trajectory. And the blue trajectory that you see here is the parent function of f of x squared. The pink is if you are multiplying it by a scalar of some value greater than 0 but less than 1, so a proper fraction. Now, if you have a proper fraction coefficient, leading coefficient that is, then you're going to be compressing your quadratic function, and it'll look a little bit flatter in comparison to the parent. So now off to the side, I've gone ahead and given myself a vertical line in this neon green, because what I wanted to do was kind of explain why this is the case, so that maybe we can have a better understanding of what these stretching versus compression does. So consider when the input value is a 1. Now that's going to be indicative of what's going on with this neon green line. When the input value or x value is 1, what's the corresponding output values for these 3 different trajectories? So hopefully you guys can see what I'm talking about. And if it's a little bit hard to see, Let me go ahead and zoom in on this business. I want to zoom in more than that. Let's go like 400%. See what that does. Oh yeah, much better. Okay, so it is a little bit fuzzy, but we can see that right here, the corresponding output values, right, when it's an input value of 1, we saw earlier when we were just plotting the x squared function that the output is 1, 2. That's right here with the blue trajectory. That's the ordered pair 1, 1, okay? Now, if we are having that, right, then the output value should be 1/2 at 1, and indeed that's the case here. So your output values are going to be smaller in comparison to your output values for your parent function when, of course, you have this, pardon me there, proper fraction scalar in front of your function, okay? But if you have a value greater than 1, then you're going to be 3 times that much in this particular example with the black trajectory compared to the parent function. The parent function's output is a 1. The parent function's manipulation, the stretching manipulation, having a coefficient of 3, the output is now a 3, which means that each corresponding output is going to be, you know, a factor of 3 larger, so taller than the corresponding parent function. Okay, so hopefully that gives us a better understanding as to why this stretching and compressing has its effect, which may or may not, depending on how your brain works, be a little bit counterintuitive. Let me go back to an appropriate level of zoom, and we will continue our discussion. So a couple of the other things that I want to highlight from these figures that I put up here that I lifted straight out of your book is that when your coefficient, leading coefficient in your quadratic function is negative, your parabola is a downward facing, as you see here with these 3 examples, which are the mirror image of these first 3 examples in figure 16, just indicating that that negative leading coefficient is going to give you a downward facing parabola, okay? Furthermore, I wanted to highlight that the vertex and axis of symmetry relationship is as follows. Whatever the x value is of your vertex, okay, that's going to be giving you x equals that particular x value is going to give you your vertical line in the location of the axis of symmetry, okay? If you have an upward facing parabola, your vertex is your lowest point, as it says here. If you have a downward facing parabola, your vertex is going to be the highest point, okay? So just a couple of things to keep in mind here. Next, I want to go over this summary that your textbook gave you at the end of section 2.4, which I thought was a great way of just having all of the information all in one go as far as what you do step by step in order to do 2 different ways to graph a quadratic function of this form, okay? If you want to go option 1, you need to complete the square in x in order to write the quadratic function in this format right here, where we have the vertical horizontal shifting and the scaling that allows for either a stretching or compressing of the function. And then of course you graph the function in stages using the transformations. So we'll do one example like this, and we'll do another example performing the steps in option 2, in which we look at the parabola in regard to just seeing if it opens up or down, in which the a value is going to be greater than 0, less than 0, okay, and downward facing if it's less than 0. Okay, cool. Now, then we'll need to calculate the vertex, which the x value for that is going to be this formula right here. This is a very important piece of information for us, okay? In fact, I'll go ahead and box this with a beautiful, bright, hot pink color, right? This is something we definitely need to have. Although I did draw a little bit on the axis of symmetry formula, this is equally important. But luckily it's just x equals the x value of the vertex. We could just remember that and we're good. Now the vertex is an ordered pair, so the x value is the opposite of b over 2a, whereas the y or output value of the function is just going to be, you know, the output according to that function with that x value plugged in. The x value, just to be clear, is negative b over 2a. Okay, great. So yes, and the axis of symmetry, like I said before, was x equals the x value of the vertex. So that's the first three steps. The fourth step is a multi-parter, which is just talking about intercepts. Okay, so every parabola is that's either upward or downward facing is going to have a y-intercept. And so you just plug in 0 for x in order to calculate that. That's probably one of the easier things that we'll be doing in this option 2 process. In order to find the x-intercepts, if they exist, you will want to look at the discriminant. So do you guys remember the quadratic formula? And if you don't, I have fun ways to remember it, one of which is singing the, you know, the elements of the quadratic formula to the tune of, I think it's Row, Row, Row Your Boat. You guys know that song? Or no, sorry, not Row, Row, Row Your Boat. I have a different thing that's associated with that song. The quadratic formula is Pop Goes the Weasel, in which you go x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. You guys like that? Put it in your back pocket. Okay, so the thing that we want to focus on here is the item inside of this radical. So the radicand of the quadratic formula is called the discriminant, okay? Okay, and the discriminant value is going to determine how many x-intercepts you have. If the discriminant, as you can see in part A right here, is positive, then you know that you have 2 x-intercepts, and you will find them by solving the, you know, equation of the function set equal to 0. Okay, which may or may not include factoring. If it's not factorable, always go back to the quadratic formula, which I have in its entirety written here off to the side in pink. If the discriminant is equal to 0, that means the vertex is at the x-intercept. Okay, so in the vertex is something that you've already calculated, so you just go ahead and put it there. And then furthermore, if your discriminant is less than 0, there are no x-intercepts, because look, what happens if this radicand right here, in which, you know, the discriminant is something less than 0, well, that's, since it's inside of a radical, that's going to be giving us some imaginary number. We don't deal with that right now while we're in the graphing in the real, you know, coordinate plane. So we just say there's no x-intercepts. It just won't cross the x-axis. Yes, this is possible. Think about downward-facing parabola with the vertex below the x-axis. It's just never going to go above the x-axis, so it's certainly never going to cross. One other thing that I want to mention for part B is if the vertex, or sorry, if the discriminant is equal to 0, that means that we have a 0, but it has a multiplicity too. It's like, you know, just the vertex is like touching the x-axis. That's something that you'll get into a little bit later on. I just wanted to highlight that at this point because it's something that you'll see later. It doesn't have any relevance to what we're working on at the moment though, but something to look forward to. Okay, so given that you've completed step 4 and you're able to determine how many x-intercepts there are and what they are if they exist, go to step 5 and, if possible, determine an additional point by using the y-intercept and the axis of symmetry. So that is to say that if you have one point that you know has to be on the curve, and you can use the, you know, mirror image concept in order to find an additional point on the other side of the axis of symmetry, the same distance away, and lined up with that y-intercept. Okay, and then of course you plot the points and you connect them with a you know, smooth as possible curvy line. Great. So let's go ahead and practice. some of this over here. And as you can see, I've cheated a little bit by determining my curve bit, but don't let that distract you here. We are going to take this function apart via the option 1 mechanism. So option 1, let's go revisit that again just for a moment. Option was completing the square to write the quadratic form in function in this particular form. Oh, look at this. Whoops. What did I do? Let's press undo. Okay, so things are lining up the way they were. Okay, so we're going to try and get into this formulation and then use transformations to graph after that. And here we go. So completing the square here will be relatively easy for us. We don't have a constant term that we have to combine anything with. We will create the constant term and then take it away. All right, so that'll be like, and I'm just going to take this little bit here and say this is 3x squared plus 6x. Oh, actually, you know what? Scratch that. Let's actually erase this real quick, just a moment. I'm actually going to pull out the GCF first, which is 3. And I'm talking only numerical GCF. I don't also want to pull out a factor of x, which technically is part of the, if you're just blindly talking about the GCF, I just want the numerical GCF. And I will get x squared minus 2x. And then I have to figure out what to add here in order to complete the square. And then whatever it is I add, I've got to distribute through the 3 and then take the opposite of that and put it here, okay? So I have some blanks to fill out, but they're not going to be exactly, opposite here. I'll explain what I mean in just a second. So just focusing on what's going on inside the parentheses, x squared minus 2x plus 1, what do? Well, we take the b value of -2, we cut it in half, so that'll be -1, and then we square it. And what's the square of -1? Well, it's +1. So +1 goes here, but I need to recognize that if I distribute through this 3 over this perfect square trinomial that I've just created, I will have a constant value of 3. So I need to undo that constant value of 3 by subtracting off 3 here, okay? So hopefully that makes sense. And let me just make a little bit of a note off to the side here. In green, I'm just going to kind of dash this little bit and say that what I'm actually doing here is I'm adding 3 and then I'm taking 3 away. So hopefully that makes sense in everybody's mind. I don't have to go into too much detail about completing the square. And let's go ahead and just move on. If you have questions, go ahead and ask in class. Okay, so then that'll give us 3 times, let's go ahead and turn this into a squared binomial of x minus 1 quantity squared. And then it's subtracting 3 on the outside. Great. So now I have my function in the form of a times the quantity x minus h squared plus k, in which a is 3, h is 1, hold on. Oh, I think I might have, just a moment. Okay, I'm back. I just had to check my phone there. Okay, so where were we? A equals 3, h equals 1, and k equals -3. So make sure you're capturing the correct values, understanding that original format. Again, let me just off to the side maybe just remind us what it looks like. We just converted this function into the form of a times the quantity x minus h squared and then plus k, just to be clear. Okay, so knowing these things here, we can shift the vertex by 1 in the positive x direction and then down by 3. So, and then also understand that, and there's a scaling that's going on as well. We'll get to that in a second. So let's first do the vertex of, or just know that we're shifting that minimum point right there to 1, -3, and then recognize that we have a scalar of 3. So remember how on one side of the parabola, if we were having the parent function, there was no multiplier, a value was 1, we would go to find the next point over, it would be over 1 and up 1 in whichever direction, over being either to the left or to the right, and then up 1 from there, as long as it's upward facing parabola. Well, for this, we need to scale it by 3. So that means instead of just going up over 1 and then up 1, we need to go up 3, which happens to be at the origin, okay? So, boom. And then recognizing that we have, the same value is going to be mirrored on the other side. The other place where we cross the x-axis should be just up 1 and over 3 in the other direction, right? So I have my already pre-drawn curve right there, which should go through everything relatively nicely. There we go. And then, of course, we will want to also, let's just make sure that, nope, it's going to do this weird thing again. Okay, it's drawing, yes. So I want to put arrow tips at the end of my curve. And there you have it, okay? So again, complete the square to get your function into this format. Use that to determine how the vertex gets shifted, right? And really it does give you the ordered pair of the vertex, h and k being 1 and -3. That's the vertex. And use this information to know that you are stretching. Stretch. So yeah, I have a relatively skinnier looking parabola. It's upward facing. I mean, I'm getting into ideas that are actually technically option 2. You can do a little mishmash of either one once you get really comfortable with this. But essentially this was an exercise in doing the shifting and the scaling. Okay, great. Cool, so let's move on to another example, but let's focus on option 2. So let's review real quick what option 2 was. A lot of steps here. We're going to say, does it open up or down? Calculate the vertex, axis of symmetry. Discriminant's going to tell us x-intercepts. Y-intercepts, just plug in 0 for f, and maybe draw an additional point. There we go. Let's try it for this fresh example right here. All right, so right off the bat, I can tell that this is a downward facing parabola by virtue of this leading coefficient being negative. So for the first part, I'll say opens down. Since a is less than 0. Cool. Vertex, let's calculate that. Vertex. The x value for that will be opposite of b over 2a, which here is opposite of b, that'll be -3 over 2 times the a value is -3. So really these -3's cancel out, signs and all, and leave a 1 up in the numerator, and that'll give us a value of 1/2. Not always fun to plot in between tick marks. I'm talking about fractions here, but it's nothing we can't handle. I'll show you what to do. Okay, now we need to plug this 1/2 back into the function in order to get the output value. So that'll be f of 1/2, give you -3 times 1/2 squared. Sorry, let me make that negative sign a little bit more clear. Not sure if that's better or not. And then plus 3 times 1/2 minus 2. So we simplify all this stuff down, and we should get -5/4, or negative 1 1/4. I think might be a little bit more advantageous for us to think about it this way in regard to determining the location which it's plotted. So that means the vertex ordered pair is 1/2, negative 1 1/4. Okay, so if you want to see the algebra involved in this, I'm happy to demonstrate it. Otherwise, let's just go ahead and move forward. I'm kind of assuming that you guys can do that. Just in the interest of not taking too much time in this video, I'm going to skip it for now. The axis of symmetry. Symmetry is going to be at x equals 1/2. Remember, just take this value that you already calculated for your vertex, say x equals that, and that's the vertical line that gives you your axis of symmetry. Cool. So we can plot that if we want to with a dashed line. Maybe I'll go ahead and throw that in after the fact. I wasn't planning on it, but that's okay. All right, so let's talk y-intercept next. So that'll be happening when the x value is 0. So, you know, imagine plugging in a 0 here and here. These two terms just cancel out, and we're left with -2. So that'll be 0, -2 will be our y-intercept. No actual calculation required if you know the trick. And then x-intercept. Well, let's see what kind of thing we're dealing with here. So let's bust out that discriminant, the b squared minus 4ac. What value do we get there? Well, the b is 3 squared minus 4 times a, which is -3, and c, which is -2. Okay, so without even simplifying this, because this goes to 9, right? And then I'm going to be subtracting off, what, 24? I can tell that this is less than 0. So the fact that this is less than 0 tells me that there are no x-intercepts. Intercepts. Hold on. Let me go ahead and just cheat and call them ints because my spelling is terrible. No x ints. Call it good. You guys know what I mean. Yes. So that's how you can kind of relatively quickly see what you're getting into if you suspect you might be performing an exercise in futility. Just, you know, quick check of the discriminant will let you know if you need to calculate anything. In this case, we do not. So at the moment, we only have two ordered pairs that we know are going to be on this curve, and that's usually not enough information to draw a curve. Two ordered pairs would be perfect if we were just drawing a line, but a curve, you need a little bit more. So let's just first plot these 2 points, and we'll see if we can, using the axis of symmetry, determine a third point, and then we can get a better idea of how this curve goes. So let's first plot the vertex, which is at 1/2, and then down to 1 1/4, which is somewhere about there. Okay, now my dot's pretty big, so it's you know, meant to be halfway, between halfway, -1 and -2. Something like there should be fine. Remember, it opens down, but in any event, we just plot the other point, the y-intercept, which is down here. So the vertex, this first point that I plotted, I'll highlight it here, that's the tippity top. So the trajectory crosses here and continues down, and then does the same thing in a mirror image on the other side. So notice that since this, hold on, let me insert a vertical line kind of on the fly here. I'll make it like this. Let's just do a vertical line. This is not its ultimate location. I want to make it green. I'll make it thicker. And I'll make it dashed. I think that'll be a nice accent here. Okay, so here is my axis of symmetry, right? So I need to be the same distance away from this axis of symmetry, but lining up with -2 in the y-sense. So right here, it looks like, you know, half of a tick mark away should give me an additional point that I know is going to be on the trajectory, okay? And that's, you know, that's enough information for me to draw this curve, which I already cheated. I pre-drew it. So I'm just going to go ahead and line up all these things right here. Okay, and look at that beautiful curve. Downward facing parabola, okay? And it's been stretched, so it looks relatively skinny. We know that to be the case because of the value of this, what's it called, leading coefficient. And furthermore, let's draw arrow points, yeah, just to be super thorough on this bit. Okay, now this is where things get silly. How do I make it so that I can draw again? Okay, let me press pause and figure this out. God. Okay, we're back. I went ahead and drew the arrow points on the end of my curve trajectories there to indicate that they're going off into positive infinity for both of those ends. Okay, great. So that'll do it for example number 44. Now let's go ahead and switch gears a little bit and say to ourselves, well, what if we were given the visual and we were asked to come up with a function? How would we be able to take information from the functions graph and determine what the equation of the function is? Notice that we are given a parabola, and the vertex and the y-intercept are highlighted for us. They're plotted, they're labeled, so we know exactly what those values are meant to be. So let me go ahead and write down those two bits of information. The vertex is the ordered pair 2, 1, and the y-intercept is 0, 5. So you can use these two pieces of information in this form of the quadratic function that has to do with all that transformation stuff. So I'm going to go ahead and rewrite this form so we remember how it looks. And so let h be 2, k is 1, and your function, your f of x value, let that be 5, and your x value, let it be 0. So that way, the only piece of information left for you to calculate is a. Every single other variable has a value to it, so you can solve for the one variable that's left. So let's go ahead and plug and chug. That'll be 5 out here. A is the one we're solving for. X is 0 minus nh of 2. Square that, and then plus k of 1. Great, so just go ahead and use your arithmetic algebra skills in order to simplify that down, and you should get that a equals 1. I know, a little anticlimactic, huh? So there are some steps in between. Let me know if you want to see those steps. Okay, so a equaling 1, and we have h and we have k. We can go ahead and put all of that information together to start over, right, with this format here, and plug in what you now know about a, h, and k, the three unknowns. Now this will just be a 1. H we already said was 2. And then plus 1. So ultimately that'll give you one form, but it'd be better if we had it, the f of x function, even though they didn't specify that we needed to give it in the ax squared plus bx plus c format. It's just most aesthetically pleasing. So let's go ahead and simplify this. We'll get x squared minus 4x plus 4 plus 1. So our final answer with an aesthetically pleasing form for x of x, f of x that is, would be x squared minus 4x plus 5. I'll go ahead and box that up. Okay, great. So hopefully that gives us a really nice overview of all the properties associated with quadratic functions as they're getting more and more complex. And now let's dive into a section in which we're going to cover the interesting things that we might do with this, and that is creating quadratic models. And we're going to do this from verbal descriptions. There are also examples in which we use data, but that requires using your calculator, and I think we're going to try and steer clear from those as much as possible. I'm much more interested in you guys working with the algebra involved rather than just relying on a bunch of button pushing. Okay, so like I said before, depending on if you're upward facing or downward facing, you're going to be working with or being concerned with either a minimum or a maximum value, respectively. So a lot of these models are going to be trying to maximize something. So you're going to notice that most of these examples are going to be dealing with downward facing parabolas or upside down parabolas. And that's just because it exhibits a maximum. But there are instances in which you could use a regular upward facing parabola. And if you recall that suspension bridge problem that we did earlier, that would be a case in point. Okay, but the two examples that I'm going to cover actually, spoiler alert, exhibit downward facing parabolas. So let's go ahead and enclose a rectangular field by doing number 8 in section 2.6. So you will notice that Beth has 3,000 feet of fencing available in order to enclose some rectangular field, and she wants to, maximize her area. That's what we'll do for parts B and C. But before we can even do that, we need to come up with the area function. So we'll do it in terms of x, where x is the length of the rectangle. So a couple of things we want to note right off the bat is that Beth has this 3,000 feet of fencing. We're going to use that bit of information, but we want to recognize that that represents the perimeter, right, of said rectangle. If we're trying to use all of the fencing that she has, that's the assumption here. So the perimeter is going to be 3,000 feet. X is going to be the length of the rectangle, so I'll just call it length. And so even though it's advantageous to us to think about this 3,000 as being the perimeter length, we are trying to create a function in terms of area. So it'd behoove us if we knew the difference in the specific formulas, the difference between the formulas and what they are specifically for perimeter and area. So you may recognize that perimeter is equal to 2 lengths plus 2 widths, right? Sure. And we have length being represented by x. We don't know what the width is or how it might be represented. Let's, for just a moment, introduce another variable of y and say that that's the width. In doing so, we can create an equation plugging in the actual value of the perimeter and go 2 lengths plus 2 widths, and then we could solve for y. And in doing so, we will have an expression representing the width in terms of x, the other variable that's already been mentioned. So solving for y, do it in a couple of steps. You will get y equals 1,500 or 1,500 minus x. Okay, so yeah, there's some steps in between. I'll go dot, dot, dot. Okay, so keeping that in mind, and this is the width. Okay, and so what is the area formula? Area equals length, right? Length times width, generally. And so if we had this in 2 variables, we would just say, oh, it's x times y, but we don't want actually that second variable that we introduced. We want to instead call it 1,500 minus x. So that means the area formula, or function rather, area in terms of length will be x times the quantity 1,500 minus x. Certainly we will want to distribute through the x and rearrange some terms. It'll be good for us to look at the function in both of these ways. Here's a convention with the leading term up in front, even though the coefficient is negative. And there you have it. Okay, so that covers part A. Done. Now for part B, they're asking for what value of x is the area the largest? Well, that would be occurring at the vertex. And how would we know that? Well, we recognize that the structure of this function is quadratic. The leading coefficient being -1 tells us that it's a downward facing parabola, which must therefore have a maximum. And the maximum value is going to be exhibited by the vertex. So let's go ahead and for part B, so this is part A right here. For part B, we're going to calculate the vertex. Now, the x value for the vertex is opposite of b over 2a. The b value being this 1500, so that's -1500 over 2 times the a value, which is -1. And that settles down to 750. Okay, so 750 is the, what is that? Well, look back at the problem. What was the context? X is the length in feet. So 750 feet is going to be, hold on just a moment. Okay, back at it. Here we go. So we just calculated the x value for the vertex, which is going to tell us the number of feet x that gives us the largest area, the length rather, that gives us the largest area. But what is the largest area possible, or the maximum area? That's going to be the function's output at that vertex value of x that was just calculated. So for part C, we'll take the area function, we'll plug in 750, and that'll give us, well, here's what it looks like plugged in. Ultimately, we could just kind of reach for our calculators, which I would be totally fine with these large numbers. And we'll go ahead and get 562,500 square feet. Ultimately, you'll just want to have nailed down the process of getting these items down. So just to be clear, for part A, here's the function of the area in terms of x. For part B, here's the x value that is the largest, in which the area is largest, and here is the maximum area for part C. Okay, let's do one more different type of example. It comes from architecture, the world of architecture. A parabolic arch has a span of 120 feet and a maximum height of 25 feet. Choose suitable rectangular coordinate axes and find the equation of the parabola. Then calculate the height of the arch at points 10 feet, 20 feet, and 40 feet from the center. Okay, so for this one, I actually decided I would freehand draw on this entire one, which will be interesting to do. Let me go ahead and change this marker to black to draw my my little bits that I want to start off with the arch. Well, actually, the trajectory, I want to do that, continue that in blue. And so it's an arch, right? That's what we're drawing. It looks like this. There we go. And the distance from here to here is what? 120 feet. And the height of the arch is 25 feet. Okay. So, oh, I'm still in black. So from here, so this is not drawn to scale at all. Okay, so what we want to do is figure out where we should be placing coordinate axes on top of this arch in order to capture everything that we want for the, easiest assessment in trying to configure what the function is of the trajectory which makes this arch. So what I recommend that you do is let the 120 feet that you see horizontally right here, let that just kind of continue and be your horizontal axis, right? Okay, so this is x, your x-axis here, and right at the center of this 120 feet, basically your axis of symmetry, I'm going to suggest that you let that be your vertical axis, your y-axis, so to speak, okay? So here's your y-axis. Okay, so if that's the case, if you go ahead and center your axes in such a way that the origin is the midpoint at this 120-foot measurement marker, then you are going to have a vertex. Actually, I want that to be blue. Vertex right here at the ordered pair 0, 25. That's your vertex. Furthermore, you'll have two x-intercepts, right? One right here, one right here. And since this entire distance is 120 feet, we're going to say that if this is the 0 marker right here, then going out the halfway distance will have you at an x-intercept of 60, 0 right there. And this one will have you at a negative 60, 0. Okay, great. So keeping that in mind, we can take the vertex and one of the x-intercepts, I guess I'll choose the 60, 0, 1, the one with the positive numbers, and we can feed that into this old gem right here, the quadratic function. Oh, sorry. Go back. Right here, right? With the shifting and scaling items, right? So go ahead and plug in your x-intercept. One of them, I'll choose the one with the positive values, and your vertex for h and k respectively, and you'll be able to calculate a, much like we did in the previous example, okay? So that'll give us 0 equals a times x is the 60, right? The x-intercept value minus h of 0. H is 0, right? Here's h, here's k. Squared plus k, which is 25. Simplifying all this down, you will get, so dot, 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 a equals 1, or negative 1 over 144. I left it in fraction format. If you have the decimal representation, that's fine too. I just figure this one is maybe it's just a little bit cleaner. Okay, so now we can take this information, couple that with our h and our k values, and we'll get the function negative 1 over 144 times x minus h is 0. So just, yeah, we'll put that in there. And we'll do some simplification. Plus 25. Okay, so that'll give us f of x is, so that'll just kind of get rid of this 0 here. I plugged it in initially just to model that format that we're looking for. So let me just, with better handwriting, write the entirety of this function. And there it is. Okay, there's the equation that we're looking for. Now that's part of the battle, right? They're like, come up with a function equation for this particular, that models this. Depending on where you lay your axes in regard to the arch in question, you might have a different answer than this, but this is what I find to be the easiest way to deal with trying to calculate this function equation. Other answers could be correct, but they'll be far more complicated in my opinion. Now we want to find the arch the height of the arch at 10 feet, 20 feet, 40 feet from the center. Awesomely, that is just a consequence of taking the function that we just created here and plugging in 10, 20, and 40. So I'll go ahead and just kind of set you up for that, but I'm not going to go into a lot of detail on that. So essentially, just for this first part, what is the height of the arch 10 feet away from the center? Well, the center happened to be, you know, the origin, so it's nice that we set it up that way, and so we won't have to put a whole lot of extra thought into it here. So it's just going to be -1 over 144 times 10 squared plus 25. So it's like, give that to your calculator, and rounding to the nearest tenth of a foot, we will get 24.3 feet for this first one. F of 20, again, it's very similar input, just put a 20 where you saw a 10 previously. And that should give you 22.2 feet. Notice it's a little bit less when you're 10 feet away, and that should be the case, right? Because the top of the arch, the exact center, is the maximum. So you should expect that as you move further and further away from that central area underneath the arch, the height of the arch is going to get smaller and smaller and smaller and smaller until, of course, the arch touches the ground. Okay, so last one. How far off the ground are you, or what's the height of the arch, rather, when you're 40 feet away from the center? -1 over 144 times 40 squared plus 25. Well, that'll get you merely a 13.9 feet. Great. So that'll answer the next part of that prompt. And we're all set. This concludes everything that I have to present on sections 2.4, 2.6. And this concludes all of the sections that are covered in exam 1. So you are now ready to finish all of the homework associated with exam 1 that's due by midnight the day before we have exam 1. And yeah, so let's go ahead and meet. Our next class meeting. Come with your questions from this lecture if you have any questions from homework, and let's prepare you for exam 1. Thanks, guys.